Right, so coming back to this topic of buffers, right? So what I want you guys to know about buffers is that it's a combination of a weak acid and its weak conjugate base. Nothing strong. There's nothing strong in a buffer. So combination of something weak plus a weak base. Okay. So that is a good buffer. Okay, there's nothing strong in a buffer. Okay, so we want to advise against. You can't make a buffer that has a strong acid and a strong base. So why would this be the case where you cannot have a strong acid or strong base in your buffer? So our cells are buffers. Our blood is a buffer. They keep the pH steady. Okay, maybe plus or minus pH 1 unit. But nothing more than that. So why is it you don't want anything strong as a constituent in your buffer? Okay. The reason why is because strong will eat everything that's weak. So if you have a strong acid in your buffer, okay, it will take away all of the base. So you have nothing to buffer against. If you have a strong base in your buffer, it will take away and eat out all the acid. So you have nothing to neutralize the base. Okay, so strong eats up everything. Okay, strong acid will eat up all the base, so you don't have any buffering capacity. A strong base will eat up all the acid, so you do not have proper buffering capacity. So anytime you want to construct a buffer, we're looking for things that are weak. Okay, classic example that we went over on Friday is acetic acid and acetate. So I would classify this as a buffer, okay? Because if you have acetic acid and acetate ion, the acid and conjugate base together in a beaker, okay, anytime you add a base, such as, I don't know, NH3, okay, the acid will neutralize it. Anytime you add an acid, let's think of a weak acid here, I don't know, HNO2, this base will neutralize that. So you have, you have wiggle room, okay, to keep the pH steady. Okay, let's say we add something strong here, okay? Okay, let's say we add strong. What are our 6 strong acids? Okay, well, one of our 6 strong acids that I'd like for you guys to know is HCl, okay? So if you had HCl here, depending on how concentrated it is, all that HCl do will take up all of this. Let's say we add a strong base to this. Okay, so a strong base typically is OH minus. Okay, an OH minus. So if you add a strong base to this, it will take away all of this until this is all gone. The strong acid will take away all of the acetate ion until this is all gone. And then as a result, your pH either will go all the way down when you add strong acid, high concentration, or your pH will go all the way up if you add strong base, depending upon how concentrated it is. Okay, very concentrated, it's going to eat up all of this. Very concentrated, I don't know, 1 molar, 2 molar. It depends on the problem. Right, so we want to keep our buffers weak as possible. The constituents or the ingredients of this buffer have to be the weak acid and a weak conjugate base. And ultimately, a buffer should do this. Think of our bodies as a buffer. Think of your cells as a buffer. Okay, they say physiologic pH is 7.4 for all the future doctors here in the audience. Okay, it's about 7.2, 7.4. And what does that do? We definitely want our pH in our bodies to be steady. And a good buffer will do that. Okay. The best buffering capacity, this is something we tend to teach in the biochem or physiology or in your biology class. The best buffering capacity, where it best serves as a buffer, okay, is when a pH is equal to pKa plus or minus 1. Okay, so that's a good rule of thumb if you're ever interested in what makes a good buffer. Okay, you want your pH to be your pKa plus or minus 1. That's when it will withstand a lot of acid or a lot of base. So as an example, if we take our buffer from our previous example, acetic acid and acetate, acetic acid and acetate, I told you guys, remember, is a good buffer because it's a weak acid with a weak conjugate base. Okay, this is a buffer. So the pKa of acetic acid is 4.76. Okay, this is something I just happen to know. It's not something you really need to memorize. So at what regions is acetic acid and acetate a good buffer? Okay, it's a good buffer between 3.76 and 5.76 when the pH is equal to that. So if your pH is between 3.76 and 5.76, this is a very good buffer. So it can withstand a lot of pH. Where did I get 3.76 and 5.76? I got it from this kind of rule of thumb that maybe you should keep in the back of your mind, especially if you're going to go into, these higher level chemistry classes or, the biology, physiology, anatomies, what have you. The best buffer is when the pKa plus or minus 1. Your pH is equal to the pKa plus or minus 1. This is the acetic acid acetate buffer. All right, so now we're going to go into another topic here, something that's totally different, and that is titrations. Okay, do you guys know what a titration is? Did you take Chem 1? Or you did the titrations? Okay, if you did Chem 1, there's a, my Chem 1 class did this. They did a titration with vinegar, right? So the idea behind a titration is that you'll have a long piece of glassware. Okay, it's called a burette. Okay, inside this burette, okay, we're going to put the titrant. Okay, that's what you're going to add, drop by drop by drop by drop by drop, okay, into a flask. And inside the flask, we will have the recipient of the titrant. This is called the titrand. Okay, titrant goes to titrand. Okay. So we will do several problems for your homeworks next week. So next week we'll have a lab this week, but next week you won't have a lab. You'll do these titration problems. So this is something I'm telling you for next week, not this week. This is something you definitely want to work together with your group and teach from each other and learn from each other, because it's a whole expansive set of titration problems and KSP problems, so it's a good practice. But what we will do, and what you'll do next week for your problem set, is we'll have different permutations. So here we'll have a strong acid or a strong base that we titrate. Okay, that we titrate against something here that's a weak acid or a weak base. Okay, obviously you do a strong acid to a weak base, or you do a strong base to a weak acid. Okay, titrating acid to acid is pointless. Titrating base to base is pointless. What we want to do is titrate acid to base or base to acid. Okay. All right. So we did one in Chem 1, and if you did happen to have Chem 1 here, But we didn't go into a lot of details in Chem 1. You just did it. Oh, wow, the color changes, and so on and so forth. Oh, wow, I saw the equivalence point. Okay, now we'll go into some in-depth problems, okay, which can be kind of a pain. I get it for some of our students. But we'll go ahead and do some problems. Let's begin now on page 6 here. Okay, acid-base titration problems. All right, so here we go. Are you guys ready? We'll do a series of acid-base titration problems. And let's begin with example number 3 here. Okay. Exactly 100 mLs of HNO2. This is a weak acid called nitrous acid. Is titrated with 0.10 NaOH. Okay, is that a strong base or a weak base? Okay, without looking here, you should know it's a strong base. Okay, OH minus. And nitrous acid is a weak acid because it's not one of our 6. Okay, it's not one of our 6. Okay, so 100 mLs of 0.10 molar, moles over a liter, is titrated with 0.10 molar NaOH. Okay, so you can imagine the burette, that long glass tube. Okay, we'll do a titration Wednesday. But the long glass tube is called a burette. Here we're going to put in NaOH, whose concentration is 0.10 molar. Okay. This is going to serve as our titrant. Okay, we add piece by piece, drop by drop by drop, into the titrand. Okay, sitting there all alone is 0.10 molar weak acid HNO2. Okay, 100 mLs. So this is the setup for this acid-base titration problem. We have a strong base here that we're going to slowly, very, very slowly and incrementally add to this flask sitting here all by itself a weak acid, okay, HNO2. Okay, part A, we're adding nothing. Okay, we're adding nothing. What is the initial pH of this 100 ml, 0.10 molar HNO2? Okay, so the Ka for HNO2, I'll give you this. And I have this in my notes here. 4.5 times 10 to the minus 5. 10 to the minus 4, I'm sorry, 10 to the minus 4. Okay, so that's something I will give you. All right, so we have 100 mLs of 0.10 molar HNO2 sitting there. Okay, what is the initial pH? All right, so this HNO2 reacts with water. Okay, in an equilibrium. Okay, HNO2 is an acid, and acids give up protons. And we will get H3O plus NO2 minus. And this H3O plus is aqueous, this NO2 minus is aqueous. Okay, just for testing purposes, just to refresh our memory, what is the acid and base here? Okay, well, obviously HNO2 is the acid because, you know, it's called nitrous acid. Okay, what's the base here? Water. Okay, now comes a question for you guys. What is the conjugate base for HNO2? Okay, so this should be kind of intuitive. That's the conjugate base. And what's the conjugate acid? What's acid for H2O, water? Okay, hydromonium ion or H3O plus. All right. right, we have 0.10 molar. Okay, water is a liquid, so don't worry about it. This is 0, 0. This is minus x, plus x, plus x. Okay, so at equilibrium with our ice table, this will be 0.10 minus x. This will be plus x. This will be plus x, excuse me. Okay, let's plug these equilibrium values into the equilibrium constant. I'm going to move my table right here. Okay, I'm going to move it back up just for space purposes. Ka is equal to products over reactants. Ka is 4.5 times 10 to the minus 4. Okay, what is H plus at equilibrium? X, what is NO2 minus at equilibrium? It too is X. What is this at equilibrium? 0.10 minus X. So X times X is X squared. 0.10 minus X. Okay, so we'll assume X is small. You can do this on the test or the exam. I will not have you do the quadratic to solve for X. Okay, so 0.10 minus X is about 0.10. So this will be 4.5 times 10 to the minus 4 equals x squared divided by 0.10. Let's solve for x. 4.5 times 10 to the minus 4 times 0.10. Okay, we'll square root that to give us x. And what is that on our calculator? Okay, just to save some time, I'm getting 6.71 times 10 to the minus 3. Is that something you got? Okay. Thank you, calculator person Allison. 6.71 times 10 to the minus 3. What does this mean? This x represents this x, which is the concentration of H3O plus, and then our pH is minus the log of H3O plus, or H plus, equals minus the log of 6.71 times 10 to the minus 3. Are you guys getting 2.17? Okay, 2.17. Alright, so this should be review from our previous chapters. Okay, now we will add, they're going to add a whole bunch here. They're going to add 80 mLs of NaOH. Okay, so they're going to add 80 mLs of NaOH here. Alright, so how will we do this? Okay. First of all, we need to understand that OH minus is a strong base, and we need to understand that HNO2 is a weak acid. So this is the reaction that occurs once you add OH minus. Remember, Na plus is just spectator ion. Don't worry about it. Okay? Don't let that fool you or trick you. Na plus doesn't do anything. So we have our HNO2 here. Okay, it's going to react with OH minus. Okay. We are at an equilibrium, and this is a strong base, so it's going to grab. Okay, it's going to grab, and it's going to abstract this proton, giving you NO2 minus plus water. Water is always a liquid. So let's just review here for a second. What is our acid and what is our base? Okay, what is our acid? Okay, well, obviously HNO2 is our acid. Okay, what is our base? Okay, anytime you see OH minus, you got to think base. In fact, it's a strong base. Okay, what is the conjugate base to this acid HNO2? What is the conjugate? NO2 minus. This is called a nitrite ion. And what is the conjugate acid to OH minus? Water. Okay. So now we need to figure out, once you add 80 mLs to here, what is the concentrations after mixing? Okay, so we'll do the concentration after mixing. Okay, once we add 80 mLs here, we have two components in the reaction. Okay, we have OH minus, and let's figure out the concentration after mixing. So we added 80 mLs. What is the concentration of NaOH? It's 0.1 molar. And what's our total volume after we add 80 mLs to 100 mLs? What's our total? What's 100 plus 80? 180 mLs. Okay. The mils cancel. So what's 80 times 0.1? 80 times 0.1 should be 8. Right or wrong? Okay, divided by 180. Okay, 0.0444 molar. Okay. In our ice table, that's the concentration of OH minus after mixing. The second component we have here is HNO2. Okay, realize that we have 80 ml, we have 100 mLs, 100. We have 100 mLs of 0.1 molar HNO2. Okay, what's our total volume after mixing? We have 100 mLs of 0.10 molar HNO2. What's our total volume after we mix these two guys together? What's 100 plus 80? Okay, 180. Okay, do you guys know how I'm getting the 180? Do you? 100 mLs of HNO2 plus 80. Guys know? So we take 80 mLs times 0.1 molar, 80 mLs of NaOH times 0.10 molar. Okay. Okay, we added 80 mils to this, to the flask that's already at 100 mils, so the total volume is 180. 100 mils of 0.10 molar. We have 100 mils here. Okay, we added 80 mils, so the total volume here is 180. All right, so the mils cancel. So 100 times 0.1 divided by 180. Okay, 0.0556 molar. Okay. So 100 mils of 0.10 molar HNO2 in here, divided by the total volume, will give us the HNO2 concentration after these two have come together and mixed. 80 mils of 0.10 molar NaOH divided by the total volume, which is 100 plus 80, 180, will give us the concentration inside this flask after 80 milliliters have been added. Okay, so this is how you get the concentrations after you mix them. All right, so this is our concentration of HNO2. This is our concentration of OH minus, which is a strong base. All right, so now here's a question for you guys. Okay, how much of this strong base will eat up this weak acid? How much? Will it eat up, how much? How much would you think? It's a strong base, remember, and a weak acid. Well, how much will it eat up? All of it. Okay, you took the words right out of my mouth. Okay, it eats all of it. Why will it eat all of this acid? Why? Because it's a strong base. That's what it will do, right? A strong base will eat up all of this weak acid. So how much is all of it, Allison? Is all of it 0.0556?
Well, that's the concentration. Yeah.
Can it eat up 0.0556? You only have 0.0444. So how much will it eat up? What is all of it, as you correctly mentioned? Okay, all of it is 0.0444. Okay, that's all of it. All of it is 0.0444. It's a strong base. It eats up everything, all of the weak acid, everything. Okay, every last bit. Not every last bit of it is 0.0444. Why won't it take up 0.0556? Because you don't have 0.0556. How much do you have of the strong base? Okay, we have 0.0444. Okay, after we calculated the concentration when we mixed these guys up together. So this becomes 0. 0.0556 minus 0.0444 is I can do this on my head, 0.112 molar, and this is 0.0444 a molar. All right, what do you guys think we have here? When we have in this flask, we have a combination of HNO2 and NO2. What do we have? What is that thing called? When we have the weak acid and its conjugate together. What do we call those things? Okay. When we have 0.0112 of the weak acid, 0.0444 of its conjugate weak base, what is that called? When they're both in the same beaker, same flask. What do we call that? It keeps the pH level. A buffer. Okay, so what equation do we use for buffers? Hasselbalch equation, yes. So to get the pH, when 80 mils of NaOH is added, we'll use the Henderson-Hasselbalch equation. Because we got some of the acid, we got some of the base, so pH here is equal to minus the log of Ka. Ka is 4.5 times 10 to the minus 4 plus log. What's the concentration of NO2 minus at equilibrium? 0.0444. Okay, what is the concentration of HNO2 at equilibrium? 0.0112. And this is our answer. Okay, what we put in our calculator. Here we're using the Henderson-Hasselbalch equation. All right, so let's do this piece by piece on our calculator. Okay, 0.0444 divided by 0.0112. Okay, we'll take the log of that, right? 0.598. Okay, I'll do it again. Okay, 0.0444 divided by 0.0112. Okay, log of that. Okay, and then minus the log of 4.54 times 10 to the minus 4, negative log 4.5 times 10 to the minus 4. 3.347. I'll put some extra digits in there. 3.347 plus 0.598. I'm getting about 3.94 as my final answer. Okay, 3.94. Okay, so that's part B. Part C is something that's very interesting. Let's do part C here. Okay, on page 7, part C is asking for what is the pH at the equivalence point. Okay, at the equivalence point. Okay, so what is the definition of equivalence point? Okay, I'll just call it EP. Equivalence point is where the concentration of the titrant equals concentration of the titrand. Okay, the concentration of both of those are equal to one another. Okay, so all of the NaOH has reacted with all of the HNO2. Nothing in excess remains. Essentially, you've added enough NaOH to react with all of the HNO2. And when I say NaOH, I mean all of the OH minus has reacted with the HNO2. Okay, when I say HNO2, I'm really talking about the H plus ion. Alright, so what is the pH at the equivalence point? So we'll first do M1V1 equals M2V2. Okay, so this M1V1 on the left is for the HNO2, and this M2V2 on the right is for NaOH. Okay, so in the problem we started out with, in pink, 100 mils of 0.1 molar HNO2. So 0.1 molar, 100 mils. Okay. What is the concentration of NaOH that we titrate against? That's in yellow as 0.10 molar. Okay, so what is V2? Okay, so solving for V2, 0.1 molar times 100 divided by 0.10 molar gives us 100 mLs. So it takes 100 mLs of 0.10 molar NaOH to completely react with 100 mLs of 0.10 molar HNO2. Okay. All right, so like before, we'll do the concentration after mixing. Okay, we'll first do OH minus. Okay, so we have 100 ml of 0.10 molar NaOH. What's our total volume after we mix these two up? What's our total volume? Takes 100 ml of 0.1 molar to completely react with 100 ml of 0.1 molar weak acid. So what's our total volume? What's 100 plus 100? Okay, 200 ml. Okay, I can do that in my head. This is 0.050 molar. Is the concentration of OH minus. Okay, what's the concentration of HNO2? It's the equivalence point. So what's its concentration? The same. Very good, Michael. 0.050 molar. Okay. All right, we'll do our equation here. NO2 minus, NO2 minus. Okay, the same equation as we had before. What's our concentration of strong base OH minus? 0.050 molar. What's our concentration of HNO2? 0.050 molar. Water is a liquid. This is 0. So Allison, I'll ask you this. How much of this OH minus will eat or consume this HNO2? How much of it? It's a strong base with a weak acid.
All of it.
All of it. So what is all of it here?
0.0.
All of it is 0.050 molar. But we have a problem here. And what is our problem? What is our problem? We got a bunch of zeros here. How are we going to calculate the pH? Okay. What do we do now? This is a problem at our equivalence point. What can we do? Are we stuck? Okay. Let me give you a hint. Okay, you see this arrow? Okay, what can we do to calculate the pH? Does this equation go this way? But where else can it go? That way. Okay, so to calculate the pH and to answer this question, what is the pH at the equivalence point? We will not use this reaction, but which reaction will we use? The reaction going this way, the back reaction. Okay, so use the back reaction to calculate the pH at the equivalence points. So at the equivalence point, this is equal to this. So when you do the strong base eats up all of the weak acid, you get 0 and 0. Okay? So to answer the question and get the pH, we'll use the back reactions, because some of it will go back this way. It's in equilibrium. So some of it will go back this way, okay? And we'll utilize that part of the reaction that goes the reverse to calculate the pH. Actually, what will we calculate first? Not the pH, but the what? Okay, we'll calculate the POH first. Okay, so let's use the back reaction at the equivalence point, or use the reverse reaction. Okay, so what is our back reaction here? It's going to be NO2 plus H2O liquid goes to HNO2 plus OH minus. And we know the NO2 minus is what concentration? 0.050. Okay, we don't care about water because it's a liquid. 0, 0. This will be minus X plus X plus X. So at equilibrium, this will be 0.050 minus X plus X plus X. Okay, what is our equilibrium here? Is it Ka? Would this be Ka? Okay, how can it be Ka? You're making H plus. What will it be? Kb, very good. But how do we get Kb, Aisha? Okay, how will we get Kb? Okay. You guys remember this equation? Ka times Kb is equal to Kw. Okay? Ka times Kb is equal to Kw. So Kw, this is something I would maybe, especially if you're going to move forward and take higher level classes, maybe memorize Kw, 1.00 times 10 to the minus 14. Ka, I just have Ka. Yeah, Ka I gave you as 4.5 times 10 to the minus 4, so that's given. You don't have to memorize that. For this specific acid called HNO2. So Kw divided by Ka is equal to Kb. Ka we gave you as 4.5 times 10 to the minus 4. Okay, so what is Kb now? .22 times 10 to the minus 11. Okay, that's a very, very small number, which means most of the reaction stays on the left-hand side. It's a very small number. Very little goes this way. All right, we have 6 more minutes here. So let's plug it into our Kb equation. Kb is OH minus times HNO2 divided by NO2 minus. Kb is 2.22 times 10 to the minus 11 equals OH is X, HNO2 is X, X times X is X squared, NO2 minus is 0.050 minus X. Okay, you can definitely assume X is small. You know why? Because 2.22 times 10 to the minus 11 is super, super, super small. So very little is going this way, but enough for us to register a POH and give us a pH. So assume X is small, 0.050 minus X is about 0.050. 2.22 times 10 to the minus 11 times 0.050. Okay, let's square root that to give us x. Okay, what do you guys get when you do that on your calculator? 1.05 times 10 to the minus 6 molar. Okay, that is x. Okay, that is x. But what does x really symbolize? Okay, x really symbolizes this x, which is the concentration of OH minus. So let's first calculate the POH. So POH is minus the log of OH minus, which is minus the log of 1.05 times 10 to the minus 6. And what is that on our calculator? .98. Okay, and this is our, no, that's not our answer. What is our answer? Okay, thank you. You guys saved me from getting my own question wrong. The pH is 14 minus 5.98, which is 8.02. Okay, 8.02. So the pH here is 8.02. Okay. So this is what you'll have to do on any quiz or exam, whatnot, in terms of getting the pH at the equivalence point. Okay, you're going to have to use the back reaction and calculate Kb. Okay.